Yeah, I think it's a bit maybe unusual topic for this seminar, at least based on what I heard from, let's say, what kind of talks you had previously here. So it will be still interesting to you. So there's a little bit of graph stuff. There is also a little bit of machine learning in the end. Most of it has nothing to do with machine learning, but it's also maybe it's necessary to motivate what we will do in the last part. So it's really mostly scientific computing, and I hope it will still be relevant or interesting for you. I'll talk about, well, these are the topics, and I'm also listing, it's obviously not just my own work, so it's work with a couple of other people. Mostly, well, my research is a lot about a class of methods that's called domain decomposition methods. And I'll show you a bit how that is related to graphs, mostly in that section. Here I will show a bit how you can use use that to solve some challenging application problems. At least to me, they are challenging. Maybe for some of the engineers, this is all very, very simple stuff, maybe. And in the end, I'll show a little bit of some, let's say, some machine learning-based techniques or how to enhance this using machine learning, especially graph neural networks. Okay, maybe I'm too. It's okay. I can also do it myself. Okay. Sorry. Yeah, this was a jump over many slides now. I don't know. I think I'll just keep using the keyboard here. Okay, so this is just briefly. So this is the research that we do in our group. I would summarize it all under the roof of scientific machine learning. I think it's classically understood as a combination of scientific computing and machine learning. I like to also add high-performance computing to it as well. This is kind of what we will be doing, and you will see different aspects of that in my presentation. So I'll first, and this really has nothing to do with graphs, or well, it's maybe somehow, but I think I first should introduce what domain decomposition methods are. And it's actually, I like to start with this remark usually because, well, it's a really old type of technique. So it's has been invented way before there were computers. I mean, it is something that is used now in computing. It's a state-of-the-art numerical method, also used for high-performance computing now. But it is actually something that has been used for very, very basic fundamental research question, because at that moment, people were still solving differential equations by hand analytically, and they knew that the solution on a rectangle exists, and it exists also on a circle. But what on this domain, which is the combination of the two? Okay, at that time, this was not clear. And then Schwarz, a German mathematician, he basically designed an algorithm that where you solve on this domain. You take this as boundary conditions, here the interior, as boundary conditions to solve on the rectangle. And then you do this in an alternating way. And he showed that this converges to the solution, actually. So it's basically an algorithm to show that existence of a solution. And now we use this to solve, for example, large-scale problems that you're not able to solve in one go on your computational resources. So you have to split it up into parts, and you can use Delft Blue or another kind of supercomputer, or even a smaller cluster to solve things. I just want to give you a little bit of motivation, or let's say intuition, for how this works. So I'll go to a very simple problem. I mean, unfortunately, there are a few differential equations in my talk, but I hope they are all, it's all relatively understandable. So here, instead of taking this domain, I take this domain. So it's just an interval. And I decompose it into two overlapping subintervals. Okay, so this is like a simplification of what we see there. So just a 1D thing. And I solve a Laplace equation. So minus second derivative is equal to 1. And the solution looks like this. Very simple. And the cool thing about this, now I can do everything really analytically. So I show you what happens if you use this algorithm. So I start with an initial guess of 0. And I would like to go to the solution, but so my error at the beginning is the solution because I start with 0. And then I do one iteration of this algorithm. So first I solve on this subdomain. I took my initial guess as boundary conditions. So this was the solution on the first domain. And then I take the solution here as boundary condition to solve on the other domain. Okay, so this is what happens after one iteration. Cool thing, if you look at errors, the errors are actually just linear then. So you can really see after 1/2 step on solving one domain, this is the error. And after 2 steps, this is the error. Okay. And now if you start, continue iterating, you see that this moves up to, let's say, getting closer to solution. The error moves down. Okay. So you see that eventually this will converge to the solution. Maybe I can move this a little bit here. This is okay. Okay, good. So this is roughly how the algorithm works. Now, well, there's a problem. I told you, let's say one motivation for using the DD now, domain decomposition, is parallelization. But this is not really a parallel algorithm that I showed you, because what I do, I first solve on one domain, and then I take that as an initial condition to solve, or as boundary condition to solve on the other domain, and then I go back. So I have not really done anything in parallel. I mean, I have split the work. I can split up work, but I cannot parallelize in the way the algorithm is designed. So what is done, or what we can do to do this, is instead of always taking, let's say, for example, for this problem, the solution of this, on both subdomains, I take the solution from the previous step. Then I can do these 2 steps at the same time. So it's almost the same algorithm. It's just that instead of n plus 1/2, I have n here as an index in both cases. So I solve both subdomains at the same time, and I take from the other subdomain the solution in the previous step. Then I can do it in parallel. Okay. So if you, well, 2 subdomains in my case, this is of course a larger machine, but this is also just to motivate. I'll show you, let's say, how to do it larger later. Okay, I do the same thing. Now I took my initial guess as in a boundary condition for both solutions. So these are the solutions on the 2 subdomain. This is how the error looks like. But now it will also converge. Okay. I mean, in each individual step, they are not continuous solutions, but you eventually again converge. One last remark that I want to make in order to give you some, let's say, intuition about this is there is some overlap here, right? I made the subdomains overlapping. It seems a little bit unnecessary to do that. But let's check what happens if I use different width of overlap in the algorithm. So this is, I only show the errors. And this is with a smaller overlap. This is with a larger overlap. And if you do the iteration, you see if the overlap is larger, you converge quicker. Okay. That also means if you think about a simulation, of course, taking more overlap means doing more work, right? Here I can solve it analytically, but in practice it means doing more work. So why would you do it? Because your algorithm will converge faster. And you can imagine that if you take the whole domain as overlap, you can solve in 1 step because you solve on one domain already everything. Okay, so that's the motivation. Now I'll come a bit more to modern, let's say, use of domain decomposition methods. Well, it's still, as I said, it's mostly scientific computing. So here I consider still a simple problem, diffusion problem. And I would typically, in order to get an accurate solution, you would like to refine your mesh. And now there are some problems because eventually, while doing that, you have to solve linear equation systems. And one nice thing about it is that they are sparse, which you can basically, the sparsity pattern corresponds to the graph corresponding to the mesh that you see here. So there is, well, the matrices can be big, but there are many zeros in the matrix. So, and now you refine to get better accuracy. And now there's a problem if you solve this like you learned in school with a LU factorization or Gaussian elimination. The cost that you do grows superlinearly. So the problem becomes twice as big. You spend more than twice the work. So at some point, you will not be able to do the work anymore. Something that you can do instead is doing iterative solvers, where in each step, you only apply your matrix once. And then, for example, if you think about, let's say, splitting this up, parallelizing this, and also, I mean, the cost, of course, in each step will be linear with respect to your matrix size, because the sparsity pattern will remain the same independent of how fine the problem is. Okay, so it's still a problem. Now I do this, So the cost increases, so I increase the problem size linearly, or actually quadratically in terms of the degrees of freedom. So the cost would grow in the same rate now if I use an iterative scheme in every iteration. But what you see is the finer the mesh, the more iteration you need. So well, somehow you didn't really gain much in that sense. So you are now able to do it every iteration in linear, let's say, complexity, but the number of iterations grows. So it's still problematic. What we would like to have is a solver where, independent of the problem size, we always get the same convergence. And I'll do that by doing so-called preconditioning technique. So I'll slightly modify my system in such a way that this system is easier to solve, hopefully, than the original one. And I want to do it in such a way that if I make my problem larger, it will always converge at the same rate. Okay, well, this has, of course, something to do with domain decomposition. So what I will be doing is I split up my domain into overlapping subdomains now. This is a very complicated 2D problem now instead of just 1D as before. So what I do is I decompose it first in a non-overlapping way, and then I add some layers of overlap. So I get an overlapping decomposition. And now, okay, there's let's say, here a little bit of math. So what essentially the preconditioner does is I take a vector that is defined globally. I restrict it to one of these overlapping subdomains. I solve my problem on that subdomain, and I take the solution and interpolate it back onto the global problem. Okay, and then I do that here in an additive way for all the subdomains. Okay, so it means that somehow I solve on local parts of the problem, and I take that as an approximation to the inverse of the whole problem. And now what happens if you do that? So these are the dashed lines. So it gets much better, but still the iteration count goes up. Right? I make my problem larger, still the iteration count goes up. So it's better, but not very good yet. So there's one missing ingredient that we need to get there, and that's something we call a core space. So we define, in addition to that, we define another mesh, which is much coarser. And then on that, like, we also assemble our problem on that mesh and solve that in addition to all these local problems. Okay, so this is a super small problem, of course. I mean, you can count the number of nodes very low. So this is very little work, but it's global work. So if my problem becomes very big, if I do it in parallel, this is something that has to be done, has to communicate with everything. And now, well, this formula would also show you that this is scalable, but you also see it more or less now in the iterations. So there's a little bit of some, let's say, in the asymptotic behavior, you see it in the beginning still increasing a little bit, but then eventually you will see now, if you refine further, will always be like they will overlap with each other, all the convergence curves. So this is a concept that is actually in every solver. If you like multigrid more than domain decomposition, the same idea. Okay, without global communication, you cannot have scalability. Okay, good. Sorry, I just jumped over this. And this is also what you see if you really go a bit larger. So if you go to, for example, 1,000 subdomains, you really see with the two-level method, iteration counts stay constant. And the more overlap, the faster. Okay, so it's all very good. Now, a little bit of some graph stuff, maybe. So something that we have been working on is a software package, which is, let's say, for these kind of solvers, which we call Frosch. In German, that means frog, actually, but the abbreviation is for fast and robust overlapping Schwarz methods. And it is something that we developed together with Sandia National Laboratory. So it's part of the Trilinos library. Maybe someone has heard that. If you know PETSI, it's roughly the same as PETSI. I don't know. Maybe someone has heard about it. Anyone heard about PETSI or Trilinos? One person. Two people. Very good. Okay, so it's a package for really high performance computing, large parallel computations. So it provides you a lot of tools for large scale parallel linear algebra and numerical linear algebra. Okay, so this solver package is part of that. And one thing that we would like to do typically what you get from an application is you get the matrix. So I want to solve a linear system. What I get is the linear system. The question is, do I get more information than that? Sometimes I don't really get more information than that. And why is that a problem? If I just go back, for example, if I want to assemble my problem on a coarse grid, I need, for example, I need to know where the coordinates of the nodes on my coarse grid are. I have to even know the coarse grid. But if someone gives me a matrix that corresponds to this, how can I come up with something like that? And that is basically where we do a little bit of some, let's say, graph-inspired things in order to make this algebraic, so in such a way that we can construct things just based on the matrix. Okay. So, and this is one concept. This is not yet a graph concept, but that is kind of something that, let's say, explains what we need in order to get this scalability. So something that we need if you want to solve, for example, a Laplace problem, this coarse grid has to be able to represent the null space of your differential equation. In the Laplace case, these are the constant functions. If you think about, for example, piecewise linear functions, you can imagine you can represent constant functions as well. If you have a complicated mesh, so what we will be doing is we have a complicated domain decomposition, and we try to construct the constant functions or something that can represent a constant function on each of the subdomains. How do we do that? Something that we know is if you solve your Laplace equation on this, let's say on this domain, and the boundary condition is 1 everywhere, the minimum energy, so if you solve with the right-hand side 0, that's the minimum energy solution, gives you 1 everywhere. I mean, the solution that has minimum energy is the one that is constant as well. Okay, so that is what we use. So we construct basically functions that are here on, let's say, on the boundaries, on parts of the boundaries 1, for example, an edge or a vertex of this decomposition. And we solve the value, the remaining values are solved by solving on the adjacent subdomains. If we sum them up, we get something that is 1 inside the subdomain. Okay? So this is the whole background of that. And to do this algebraically, we need a little bit of some, let's say we use a little bit of some graph ideas. So there are 2 different graphs that play a role here. And I'm not sure if I have the same well, notation or naming as you have, but so the 2 types of graphs, we call that a node graph and a dual graph. The node graph, for example, if this would be also already my finite element mesh or my mesh, then the node graph is really just the graph that corresponds to the mesh. So every node of the mesh is the node of the graph, and every edge of the mesh is an edge of the graph. And if you do a parallel computation, what you would typically have, you get from your, let's say, application user code, you get a matrix which is parallelly distributed based on a partitioning of that graph. So typically you get something where some of the rows, maybe one subdomain belong on one rank, this is on another rank, and so on. So this is typically how you get the parallel distribution. But there's another graph that is typically used, which is the dual graph, which is a graph in which every mesh element is a node, and there is an edge between them if 2 elements share an edge in the graph. For example, this element here and this element are nodes of the graph, and they have an edge because they share an edge in the mesh. And this graph, we kind of, if you want to assemble this matrix in finite elements, you always go over you assemble based on these elements, not based on the nodes. So this means you actually need a parallel distribution which corresponds to this partitioning of this graph. So those are the 2 things, and those are the 2 things which we assume we have, and then we do our algorithm. So the 2 main ingredients in order to design the precondition are, one is the overlapping domain decomposition. So let me discuss how we get that. So if you start with, for example, you have used some, let's say the user code, they have used some mesh partitioning, they give you something like this as an input. And now, in order to solve locally, basically we only have to find these matrices Ri. The one in the middle is your original matrix. And the Ri are just matrices that extract the subdomain from the original one. And we want to do that based on the overlapping decomposition. So something that we do is, oh, should I? Okay. Okay, so something we do now is we look at the sparsity pattern, and there's also another graph, let's say plot below later. So we look at the sparsity pattern and we add layers of nodes to those subdomains. And how can we do that? If you remember, let's say if two nodes, or here in this case, if two nodes are next to each other, if they have an edge in the matrix, this means they have an off-diagonal entry, right, based on the adjacency matrix. So you basically can easily find neighbors in your graph. So you can extend by layers of elements or layers of nodes. And this would be, if you see it in a graph, let's say graph-based view, you start with something, let's say where those nodes are all part of one subdomain. Then you would find, based on the adjacency, you would find off-diagonal entries. You would find nodes which are adjacent. And then you add all of those to your subdomains, right? And you do this in a recursive way, so you can get more and more overlapping subdomains. So this is the one thing we do. The other thing is the core space. And as I discussed a bit earlier, what we need for that is we need to find these kind of edges. So these are edges now between subdomains, okay, where two subdomains touch each other, and vertices in 2D case. Okay, so we basically have to find, let's say we have to find kind of a graph corresponding to our course, let's say to the interface components here. So the first thing we have to find is the edges and vertices here. Then, as I said, we find functions which are 1 or a constant on those edges and vertices. And then this is solving local problems. So if we can do those 3 steps, we can do this algebraically. And we do this, generally we use the dual graph of the mesh for that. Problem is if you get a matrix which is not distributed based on the dual graph, if you don't get it, you cannot really get it exactly back. But you can find approximations of that, or you can do some heuristic steps to get it. So basically, you would have something where the nodes here, which are shared by elements, you know that they belong to those different partitions of your graph. And then I can find the edges and vertices by looking at every node to how many subdomains or how many partitions they belong. Every node that belongs to 2 is on an edge of this decomposition. Every node that belongs to 4 or more than 2, that's a vertex. Okay, so you can the only thing you have to do is you have to find these equivalence classes. So one equivalence class are all the nodes that belong to the same index sets of subdomains. You find an edge, you find a vertex, or you find interior nodes. Okay, so this is, and then you can construct these things fully algebraically. And there are a couple of type of methods which can be summarized under this framework, which I will not go too much into detail here, but I don't think that is so relevant. I just want to show there are a couple of approaches which fall into this framework. Now I just want to show some results briefly, and then I hope I still have a little bit of time to show the machine learning part. So firstly, show that this works. So this is here, I scale up the problem size. So the largest problem here is 1.7 billion degrees of freedom, or nodes in this case. So it's a big problem, 64,000 API ranks. So that's, I guess, roughly 4 times Delft Blue or something. So these are a bit older computations on uQueen in Jülich, Germany, when it was still in operation. You see, we can scale up, iteration count stays constant if we increase problem size. Time goes a bit up because the course problem gets larger, and that is a global problem, as I mentioned to you. But something that we can do is we can do this preconditioning technique recursively. So instead of solving the course problem with a direct solver, we take another preconditioner to solve that. So it's like a multi-scale, multi-level approach, and then the time the iteration count is a bit higher now, but the time goes up much less because the bottleneck is not so big. Now some challenging application problems. I don't know, some application problems. So one thing, we can use the same framework to solve, for example, fluid problems. So far I've talked only about simple scalar elliptic problems. You can use this to solve fluid problems where the original problem has a block structure, but you can construct the same type of preconditioner. Now just every of the matrices appearing in your preconditioner is also a block matrix. That's about the level of detail I want to go into now, because otherwise this could be a separate talk. I just want to show you that this has some nice properties. This is a blood flow problem on an idealized artery here. And we just tested, for example, if you look at, let's say, flows where let's say at maximum flow rate, you have different Reynolds numbers. So here, the maximum Reynolds number is around 450 or 1,600. And if you use, this is a block preconditioner. So this is standard type of preconditioner. Maybe you've heard about this. It's called simple preconditioner. This is, let's say, really a standard type of thing. First, you see generally iteration counts is higher. I mean, this is scalability for larger problems or more mesh refinement. And you see that iteration count is a bit higher here. But something that you also see is if you go to higher Reynolds numbers, our method has roughly still the same convergence, whereas the other method, the iteration count goes up significantly. We have also done another problem. I mean, I showed already this, like this ice sheet, this flow of the ice image. So we've done simulations on both Antarctica and Greenland with our method. We solved two different types of problem. One is a nonlinear velocity problem. So it's a nonlinear Stokes problem. And we also coupled that with a nonlinear temperature model. So then it's a multiphysics problem as well. The difficulty is that the mesh is very anisotropic. So it's very, I mean, the ice is very thin compared to how wide it is. And we have, this is strong scaling. So I take the same problem, increase the number of MPI ranks, and I hope my time goes down, which works, I think, quite nicely for this case. This is a more difficult problem. I mean, we still, especially in the setup, it scales relatively well. But this is really more difficult problem. For example, this the colleagues at Sandia, they were not able to run it with multigrid at all. So this was kind of nice. Last type of problem I want to show as an application type problems are highly heterogeneous problems. So problems that have a microstructure, and that appears in many applications. And you can think about maybe dual phase steel applications. You could think about subsurface flow. You can even think about biomedical applications where your material parameters will vary in space. And this is, I can tell you, this is a difficult problem for a solver. So this is, again, kind of a, well, inspired by these kind of things, test problem. So it's a cube where you have a foam type microstructure. And here the solid phase has a high, here in this case, diffusivity. And this has like this transparent phase has a very low diffusivity. And if you solve this with the standard method, this problem is very ill-conditioned and the iteration count is huge. And this is a, let's say, medium-sized problem, so 100 subdomains. If you take more subdomains, it will get worse. And something that we worked on is are methods that basically give you the same convergence that you would get if the problem was completely homogeneous. And the way how we do this, to say it briefly, is again, we look at these interface components, so the edges and vertices, and we solve local eigenvalue problems there. So we compute some additional functions for our course space or for this course level. And they kind of encode these difficulties which lie in the microstructure. And then you get convergence back to basically, you can define what your condition number you would like to get. So there's a tolerance that tells you which final condition number you get. And that is kind of a tolerance for which eigenfunctions you have to choose. So it will adaptively give you more functions, so also more expensive, but it will give you a guaranteed convergence. And also a PhD student here, Felipe, he's doing this now, also implementing these, let's say, robust solvers into this parallel code. So the simulations I showed before were still small. So he did, for example, this is this SP10. So this is like a reservoir, let's say, subsurface flow problem where you have heterogeneous permeability and porosity. And you see that only if you take, let's say, those, let's say, more sophisticated techniques, you get fast convergence. And if you do, let's say, standard techniques, it doesn't work. And this also still, you see similar behavior. So this is number of iterations with problem size. And you see that if you use one of these, let's say, enhanced course problems, you get, again, scalability, and all the other methods do not scale here. Okay, as I said, I wanted to not go too much into details, also to leave time for this last bit. I think I'm a little bit late, but I think I also started a little bit like 2-3 minutes later. So I hope I'm fine. Okay, now a little bit of machine learning. But I think it was kind of also necessary to motivate all of this a little bit, because maybe it's not the domain decomposition, maybe not the most typical type of techniques. Okay, so something generally, and maybe this slide is a bit too detailed. So generally, the story now is, well, I said before, it's super, like this construction is very nice because you can do this algebraically, but it is actually quite expensive still to do, because in order to compute those basis functions, we have to solve these local problems. And they are potentially, this takes quite a lot of effort to do. And some of the methods, and I did not say that, but for example, computing these eigenvalue problems, we cannot do it algebraically, because some of the matrices we need are matrices that you cannot extract from the original matrix. Right? So and that's kind of inherent, actually. So if you can take some, let's say, matrices which come from the original one as an approximation, but then you can always find counterexamples where the method will not be robust. Okay, so something that we tried now, that we wanted to try, is to see, and I mean, you can still probably break it, but we would like to see if we can learn the way how to construct these basis functions based on just the matrix as an input, and get something that is both faster than solving problems, like really solving differential equations to compute the basis functions, and also maybe still robust. And this just, again, to say again what these two things are. One is, in order to compute the functions, we have to solve a problem. And that problem is of the size of all the nodes which are inside one subdomain. That can be many. So this we would like to make cheaper. And at the same time, this is again just let's say maybe a little bit of a repetition. So if you just take a standard core space, it will be, maybe your convergence will be slow. If you take something this is, for example, a function that corresponds to this coefficient. So you see that an adapted basis function is, for example, a function that does not decay where your diffusivity is high. Because that would be something that results in like large eigenvalues, whereas this gives you low eigenvalues, so this gives you fast convergence. Okay, so it's kind of, so you need something that knows about the structure of your problem, but of course the structure of the problem is somehow encoded in your matrix, of course, right? So we hope that we can learn this. Okay. This is just to say that, well, there have been also other related works on this. So there has been some work also on constructing coarse basis functions or constructing interpolation operators, also for multigrid methods, actually. And I think this is a relatively recent review paper, in case you're interested in this a bit more. Whereas I have to say, most of these approaches, I think all of the other approaches are not using graph neural networks, but other let's say other networks. I think some use GNNs, but some also use CNNs, some use MLPs. So it's like so this is still a bit exploratory, I would say. And so what we want to do Yeah, so we want to use graph neural networks because, as I said, what we want to use as an input is our system metrics. And as I already discussed earlier, basically the system metrics has the same structure as your node graph. So it's basically the node graph. So we would like to use graph neural networks in order to learn this. And of course, a graph neural network basically uses like message passing kind of operation. So basically it's a neighborhood information that you use. And that will also be relevant actually for, let's say, some of the things I discussed in a few minutes. And our idea in the end is because on all the subdomains, we will solve the same differential equation in order to compute the coarse basis functions. We would like to train one GNN that we can apply on every subdomain in order to compute the extension, this extension operator, right? So basically, we assume that we know our basis functions on the interface, and what we would like to have is one GNN that can give us always the values that we would need in each of the subdomains. So that's the idea. So in particular, we first do a step just on the interface. So we take, for example, nodal values, then we get the values on the edges. This is it's a 1D thing, so this is very simple. And then we extend into the interior, and for that we use a graph neural network. Okay. Then let's say just some observations or some things how it makes sense to think a little bit about including knowledge somehow into this. One thing that I mentioned to you is that we would like to make sure that we can represent constant functions. So we would like to have that all the basis functions, if we sum them up, that we get 1. So something that we do is before we plug this into our loss function, we actually compute such an average operation to make sure that the sum of all the basis functions we learn actually give us 1. Okay, so that's something we can explicitly ensure by just taking the prediction and dividing by the sum of all predictions. So you will always, if you sum them up, they will always give you 1. This is one thing. And another thing is kind of something that is actually, well, I think everyone who knows about GNNs, well, everyone here will know this, but it's kind of, let's say it's an interesting thing. So the way we do this as an initial, basically as an initial guess, we just take, we take some function which is defined on our, let's say on the subdomain. So as I said, we prescribe the values on the boundary, and we would like to predict the values in the interior. So we have to give some initial guess, something that lives here in the interior. And then depending on how many message passing steps you get, you really see that the GNN kind of is only able to learn the extension operator really in the whole subdomains if you do enough message passing, or if you use a multi-scale graph neural network, which is also something we do in practice. Actually, if the subdomains get too big, it is better to not just do 100 message passing steps, but do, let's say, add another like a coarse level of the GNN here. Of course, if you do a bit too much, it also becomes a bit unstable. Good. Just 2 more slides of results, then I'm done. Firstly, to show that this can work. So what we did first is we took one big problem. So this is maybe a big problem. So this has 64 subdomains, and this is our training data. So we just solve one problem. And because this already gives us 64 subdomains that we use as training data. Okay, so every subdomain has also multiple basis functions, of course, right? So in that sense, we already from one simulation, we get a lot of training data. And then we do a weak scalability study. So basically, this is also executing the GNN in a test case with 64 subdomains, 256, and 1024. And now I should explain the different plots. So blue is 1-level method, so that is not scalable. As I said, you need 2 levels. So you see that as you increase the number of subdomains, the convergence will get worse for the 1-level method. Use the yellow dashed line is basically if you would use our initial function here as a coarse function. this is already a partition of unity. These functions are also, well, they also represent constant functions by construction, but they are not, yeah, they're not very good. I mean, they give you kind of something reasonable, but still much worse convergence than if you use the GNN, which basically gives us the same performance as if we would do this costly construction that we did before. So we get more or less exactly the same. And now this is, well, the work in progress slide, maybe. So as I said, we would like to do this also for challenging heterogeneous problems. So this is a homogeneous problem. Now, what happens if you do the same thing for a heterogeneous problem? And basically, our GNN approach is, well, it's doing much better, for example, than one level. And it's also much better than doing, for example, just taking linear functions, which is the one that works for a homogeneous case. But we see that it gets more and more, let's say, if we scale up, it gets more difficult here for us to still approximate this. So in this case, where you take a heterogeneous problem with coefficient jumps, also for the GNN, it is more difficult to learn this properly. And it is kind of, I mean, I don't have to get the functions very correct, but if the coefficient is high and you have too much variation, whatever variation you have in the high coefficient case will directly go into your convergence. So you have to be very accurate on that part. And that is, well, of course, you can do further optimization, well, hyperparameter optimization, whatever. But I think it's better to do this maybe a bit more in a, let's say, more informed way, let's say. So I think we need to improve on our approach a bit here. Last two slides, just in case you're interested. We will do a workshop in Utrecht in June on SciML and industry. And I think we have quite a good setup of speakers. Maybe this is interesting for you. We don't have a website yet, I think. Well, it's really right now we're organizing this, but maybe you can, if this is interesting, you can keep it in mind. And there will also be a research semester at CWI. Which will have a autumn school, a workshop, and then maybe some additional talks, which are also all in the context of scientific computing and machine learning. Yeah, I will not repeat everything I said. I mean, yeah, this is kind of a summary, but yeah, I will not say more because maybe then there's time for one or two questions. Thank you very much.